So today's speaker is Dr. Longhuan Zhu. He's a postdoc from Michigan Tech University. So I'm very excited to invite him to give a talk. Longhuan and I were classmates since freshman, from freshman to PhD. So, and Longhuan did a very, he graduated, he got his bachelor degree and master degree in Tianjin University, China. And he got his PhD in University of Maine. Longhuan did a very nice work on studying the wave damping caused by vegetation and aquaculture farms. So today Longhuan will give a talk about the coastal protection using the natural based and aquaculture farms as a solution for coastal erosions and the climate change. So if you have any questions, please type in the chat or just directly ask a question at the end of Longhuan's talk. So now I'll head to Longhuan. Yep.
Okay, thank you, Dr. Liu. Yeah, I appreciate your invitation. So it is a pity that I cannot drop by in person to present my research because I have to take care of my babies. My babies too little and traveling is not convenient for us. But I think it is also very good to communicate online. Okay, so good afternoon, everyone. I'm Longhuan Zhu. I'm currently a postdoc at Michigan Tech, working with Dr. Pengfei Xue. And this presentation will cover my postdoc research and my PhD research. So I'm very glad to share my research on coast erosion and nature-based solutions with aquaculture farms to adapt to and mitigate climate change. So how does climate change influence ocean and coast? We say climate change particularly refers to the fast increase of global temperature since the 19th century due to the industrialization, which produces large amount of greenhouse gas. The climate warming hits the ocean and melts ice, yielding sea level rise. Due to air-ocean interactions, the warming ocean will induce more intense storms, which will cause serious coastal hazards such as coastal erosion, storm surge, and flooding. Supervised with sea level rise, the coastal hazards are more serious. Meanwhile, the carbon dioxide entering the ocean will cause ocean acidification, which causes ecological issues such as the forming of coral reef and oyster reefs. As we know, the ocean processes like circulation or mixing is a very complex and slow process. So that will take a long time to solve the issues induced by the climate change. That also means that the serious coastal hazards will continue for a long time. Then I will take Lake Michigan as an example to show the effects of climate change on waves and coastal erosion, as well as water level changes in Lake Michigan. So Lake Michigan is the third largest lake of the Great Lakes, and it is also the fifth largest lake in the world. It has surface area of about 58,000 square kilometers. And it has shoreline of about more than 2,600, and which is home to more than 12 million people. However, the analysis of the long-term trends of the coast erosion in the entire lake is challenging because the historic data is only available at a very few local sites, and the data is discontinuous with gaps for years to decades. So to solve this problem, we use coupled with sediment, current sediment models to generate the long-term data, where the waves were modeled with swarm, the currents were modeled with FECON, and the sediment transport was modeled using the community sediment transport model system built in FECON. We have run the model for 30 years from 1991 to 2020. To evaluate the sediment transport and coastal erosion, we divided the 5-kilometer wide coast area into 120 budget cells, which is numbered from west to east, with 60 in the south. The modeled 30-year mean longshore sediment transport was counterclockwise, with large longshore sediment transport in the south and southeast. So from and as sediment transport varies along the shoreline, so we can see for the budget cells that may be eroded or deposited depending on the sediment transport, net sediment transport in and out of the budget. So here, the red colors indicates the erosion at the budget cell, and the blue color indicates depositions budget cells. So from the west, along the shoreline of Wisconsin, we can see in the north part, probably north to the Concordia University, is more erosion spots, and in the south there are more erosion spots. And along the shoreline of Illinois state, we can see that the shoreline is the coastal area is continuously eroded, and since this deposition area in the along the west shore of Indiana state, and since the shoreline is eroded around along the eastern shore of Indiana, and then in the west shore of Michigan state, we can see that the erosion deposition occurred staggeringly. So with the data, we in order to analyze the long-term change of the coast erosion, we did the 10-year moving mean for the wind speed, wave height, and coast erosion. So why? Because we cannot find the statistically significant trend, linear trend, if we did not do the moving average, and the underlying mechanisms, underlying physics for the moving average. I will explain the physics later. So the results showed that in for the entire 5-kilometer wide shoreline, the coastal erosion accelerated since 2010, and this is consistent with increase of wind speed and waves. And what is interesting is that the increase of coastal waves and coastal erosions are highly correlated with the increase of water level, shown here, and the correlation coefficients are larger than 0.7. And we found that the increase of the waves or the coastal erosion is about 3 years ahead of the increase of the water level. So the high correlations between the waves and water levels cannot it's not directly caused by the causal relationship between them, but it can reflect the effects of regional climate change on Lake Michigan. So associated with climate change, there are more storms which will generate the waves instantly, so resulting the suspension of sediment, and then the sediment is transported, which will cause coast erosion. And at the meantime, the storms will increase the precipitation, and which will cause changes of water level by hydrologic cycle. As the hydrologic cycle is a complex and slow process, which may take several months to several years. So we can see that the water level is behind the change of the waves. And thus the relationship, the time lag relationship between the waves and water levels can be used to predict the water level change using the measured wave data. And that is very useful. And then as the hydraulic cycle is is a cumulative process. The water level is reflected as a cumulative effects of the precipitation. So, but however, the waves happens instantly. So when we study the relationship between the waves and the water level, we should do the moving average for the waves to consider more years. So that the periods of the waves and the water level can be matched. So that is why we will using the moving average wave heights. We can find the high correlations between the wave height and the water level. So, and this tells us the effects of climate change on the environmental factors are very complicated, and the effects on the environmental factors may be different. The environmental factors may respect at a different time. So we can use time lag between the environmental factors to predict the change of one environmental factor from the known environmental factors, and that can give us time to prepare for the climate change. And then, although the total coastal erosion increased significantly in the past decade, the erosion and deposition at local budget cells present different trends. So we first did this linear analysis to show the trend of the local coastal erosion and deposition. We found, although there are only a few sites that shows statistically significant linear trends, but the results indicates that the coastal erosion and deposition decreased in the western lake and while increased in the eastern lake. To further demonstrate the spatial pattern of the coastal erosion and deposition, we did the region shift analysis. So we checked the change of the coastal erosion and the deposition from two periods. The first period is from 2000 to 2013 with low water level, and the other period is from is during 2014 to 2020 with high water level. And the year 2014 corresponding to the strong Illinois events happened in 2014 to 2016. So we found, and this can give us a clear information that the coastal erosion and deposition decreased in the Western Lake and increase in the Eastern Lake. So at the moment, we have analyzed the changes of the coastal erosion induced by the sediment resuspension and transport. Now we'll compare the results with historical shoreline research and acquisition mapped by John Pope in 1999. As shown in the figure, where the inner cells, the modeled coastal erosion and deposition, while the 6 lines indicates the shoreline change, and the outer lines indicates the shoreline types. So for most part of the regions, the modeled coastal erosion and deposition are consistent with the shoreline changes. For example, in the southwestern lake, we can see that the coastal erosion indicates recession of the shoreline, and the deposition here also we can see the accretion of the shoreline. The discrepancies in the in the western lake and the eastern lake, probably here the shoreline is recession, but it's a coastal area show the deposition. Probably it is caused by some the size of the budget cells. At present, we use the 5 kilometer wide budget cells, but if we only analyze the 1 kilometer wide cells, we can see that this areas also is suffering erosion, which is consistent with the shoreline change. Now we have noticed that the coastal erosion in Lake Michigan accelerated in the past 10 years. So how can we reduce erosion and protect our shoreline? So traditionally, we'll use like the artificial coastal defense structures, like seawalls, or barriers, grounds, or breakwaters. However, these traditional artificial coastal defense structures may do harm to the ecosystems, and in addition, these structures are not sustainable because due to climate change, for example, like the sea level rise, and if we need to make some artificial coastal defense structures still work, then we need to adjust probably the height of the seawalls, and that may take that will be more expensive. So nowadays, the researchers are looking for nature-based solutions, which use the natural materials such as wrecks, coral reefs, oyster reefs, and vegetations. These natural materials are ecological and sustainable. And we know that seaweed, like the seaweed and the shellfish aquaculture structures, that also have the green features, and they are also ecological and sustainable for the environment. And in addition, this aquaculture can also provide seafood for us, and it can bring economic benefits. However, the coastal protection properties of these aquaculture structures are not studied yet. So my PhD thesis is focused on the wave attenuation of wave attenuation by aquaculture structures. So before I'm going to analyze wave attenuation by aquaculture structures, let's look at the structures of Longline kelp farm. So as shown on the right, this is a long line of kelps. The kelps grows on the long lines, and the long line is supported by buoys and mooring lines, so that the kelps can be suspended in the water column. And this is a figure of the long line underwater, which is taken by Dr. Hayden from Woods Hole. So we know that the kelp is a very flexible structure like vegetables, vegetations. So the motion of the kelp is very complicated. It shows like a wave-like motion, and it's challenging to model the motion of the flexible blade. So, for example, this is a model result from Ruha and Neff. And here's the black lines indicates the measured posture of the vegetation at one time, and the magenta lines indicates the model result from Luhe and Neff's model. So this is for the 1/4 wave period and half wave period, and it's 1/3 wave period. So we can see that there's a big discrepancy between the model results and the measured vegetation, measured posture of the vegetation. So why is there big discrepancy? So I'm working on to improve the model, and then I introduced the cable model. So we know that the blade motion is induced by the hydrodynamic forces, which includes the drag, friction, vertical buoyancy, and added mass force. And when we check the governing equations in Luha's model, we found that when they calculated this issue, when they calculated the added mass force, so the added mass force is proportional to the related acceleration between the vegetation motion and the wave velocity. And in their model, they used the local. They used the global coordinate system, like the XZ, the fixed global coordinate system to describe the wave velocity, and they used the local Lagrangian coordinate system, which is fixed on the blade to describe the motion, the velocity of the blade. And in the in computation of the related acceleration, they used the they decomposed the acceleration in the global acceleration, the wave acceleration defined in the global coordinate system to the local Lagrangian coordinate system, but they did not consider but we know the blade will move so that the local coordinate systems will rotate. That will cause inertial force, which is not considered in their model. So we modified this formula by considering the inertial force due to the rotation of the local coordinate system induced by blade motion. And we also did some other modifications, but they are not as important as this one, as the modification of the added mass force. And here is results from our model with modifications, which is shown by the green colors. So we know after the modifications, the results has been improved by about 80% when compared to the postures for the posture comparisons. So, and this model can capture the asymmetry wave-like motion. Then we know we see that the motion is asymmetric, and we found so the asymmetry can be induced by the nonlinearity of waves, but we found that the blade motion can be also asymmetric in linear waves. And we also did the research on the mechanisms for the asymmetry motion of the blade. So we know that the water particles in waves is like circle, if the waves propagate from the left to the right, then that will be a clockwise circle. So at this point, at the beginning of the waves, so the blade will follow the water particles to move to the right, and then the water particles to go down a little, and then the blade will go down, and then now the water particles totally go down, so the blade also go down, driven by the waves, and then the water particles go back, so the blade begin to go back, and then the blade follows the water velocity to go back, and finally go back to this point. But we know that because we know that the horizontal component of the water particles is symmetric, right? You know, at the first half of the wave period, the horizontal velocity goes to the right, and in the second half of the halfway period, the horizontal velocity goes to the left. So they are balanced, but the vertical component of the water wave, the water particle velocity, it is downward in the right and upward in the left, so that would cause clockwise momentum, which causes the asymmetry of the blade motion. And this blade motion in deep water waves and shallow water waves. We know that in deep water waves, vertical component of the wave water particle velocity is very important. So we can see that the blade motion is very symmetric. But in shallow water waves, the vertical component of the waves is very little. So the blade becomes more symmetric. Why is the asymmetry motion is very important? Here we'll look at a video of the suspended suspended blade, such as like the kelp. So due to the asymmetry of the motion, we can see that the blade inclines to the left, and then if the asymmetry is very serious, the blade will roll over to the along the long line, so that we cause the breakage of the blade. And the asymmetry of the blade motion can also provide a shelter to inhibit the sediment suspension. So probably that will help to reduce the erosion. And because of the asymmetries, the blade is stretched on the side, but pressure on this side, so that may change the morphology or influence the fatigue strength of the blade. Then we implemented the blade dynamics into a CFD model, the open form, and then we can study the interactions between the blades and the flow. And then we extended the model to a 3D case. So by considering the long lines, the buoys, the mooring lines, so that be more realistic to predict the dynamics of a long line systems in the field. Okay, now let's look at the wave attenuation by kelp farms. We made the elastic modulus of the blade, and then we did the dynamic scaling to model the kelp. Because kelp is very it's huge, so we cannot do the full scale. I mean, use the real kelp to analyze wave attenuation in the lab. So we did this downscale physical experiments at MIT, and this is long line of kelp blades, and this is our model. We use the silicon film to model the blade by considering the dynamic similarity, and this is our results, and this is our model. And here shows wave attenuation properties of the kelp farms. If we look at figure A, so the EDA, that is the wave and energy dissipation ratio. So we can see that the wave energy decrease with this is a wavelength. So that means suspended kelp farms is more applicable for damping short waves. And this is different from the submerged vegetation. I will talk more later. And this one is wave vegetation versus instant wave height. So we can see that the wave vegetation is not sensitive to the wave height. And this is wave attenuation changes is blade length. So increase the blade length, that's the wave attenuation become more. And this is distance from the surface. So if the kelp is more close to the surface and the wave attenuation is more promising. And we also check the sensitivity of the wave attenuation to the elasticity modulus. And we found that if the elasticity modulus increased from 1 megapart to 20 megaparts, the wave attenuation only increased by 15%. So that means the wave attenuation is not sensitive to the elasticity of the blade. But we found that the plant density and the number of long lines are more crucial to increase the wave attenuation. For example, for 200 long lines with 400 plants per meter, if the kelp grows to 1 meter long, it can reduce like 47% wave energy. Now we have the models. Can we directly input the models into the large scales in the field? Actually, it is we cannot do it right now because CFD computation is very expensive. So traditionally, we use this model to calculate a roughness coefficient and then implement the roughness coefficient large scale wave model. And for some researchers, they may use consider the vegetation as rigid and then use the wave dissipation as a synchrotron into the wave model. They will use the bow-drag coefficient or effective blade length to consider the effects of the blade motion. However, I'm thinking if we can do a comparison, so that means if we can consider the blade motion, but probably not fully resolve the blade motion, and decrease the computing. So to achieve this goal, we use the analytic solutions by linearizing the blade motion. Here's the results. We'll take the submerged vegetation as an example. The red line is the motion from the full nonlinear results. So we can see that there's a big difference, but the wave attenuation in the upper side is very small, like 0. So although the blade motion is quite different for the upper part of the blade, but this part of blade has little contribution to the wave attenuation. So we can use and then linearized blade motion to analyze the wave attenuation. And we also validate this hypothesis using the experimental data. Here shows the numerical results, and the numerical numerical underestimates the wave attenuation by like 11%. This is analytical model. It's underestimated a little larger, like 27%, but it's acceptable for engineering application. And then we can do some modification to improve the analytical model, which has a similar result with the numerical model. So the previous analysis is for regular waves in lab experiments, but in the field, it is like random waves. So we extend our model for the random waves, which is a frequency-dependent wave attenuation model. And we validate the model using the experiments by Jack Hobson and his comparison, and the comparison is very good. And finally, we'll analyze wave attenuation capacity of aquaculture farms, mussel farms in the storm events. And we analyzed the case at the Saco Bay in Maine during this storm events, the water level. So here shows the water level. That is, the tide, the range is about 3.3 meters. The water level change very seriously. And this is the wave height, and the largest wave height is about 3.6 meter. And the wave period is from 5 to 13 seconds. And we choose the mussel farms, and then we compared with submerged aquatic vegetation to show the characteristics of these two kinds of cannabis. And we analyzed the wave attenuation at the same water depths. And here, so from this figure, the blue lines indicates the wave attenuation by mussel farms, and the red lines indicates the wave attenuation by the submerged aquatic vegetation. So for shorter waves, like the with period shorter than 10 seconds, we can see that the wave attenuation by mussel farms are larger than the vegetation. And here's wave attenuation, the attenuation of the spectrum. So we can see that for the upper layer, the blue lines indicates the wave attenuation by mussel farms. So the wave attenuation by the mussel farms is more serious, promising for shorter waves. And for submerged vegetation, that is more promising for longer waves. And then we consider analyzed the combination of the mussel farms offshore and the nearshore submerged aquatic vegetation. So we know here's a red line indicates wave attenuation by submerged aquatic vegetation. The submerged aquatic vegetation is sensitive to the water level change, and the wave attenuation can drop by 50% from low tide to high tide. However, the mussel farms is not sensitive, as shown by the red line, blue lines. If we add the mussel farms offshore, the wave attenuation by the nearshore vegetation can be improved by 60%. And for shorter waves, especially at high tide, the improvement can be 185%. So the conjunction of the combination of the mussel farms offshore and the nearshore submerged vegetation could be more promising wave attenuation strategies. So here's conclusions. We found that the coastal erosion in Lake Michigan accelerated due to the climate change, and we prefer to use nature-based solutions to mitigate the effects of climate change and protect our shorelines. And the large aquaculture farms could be an option. And we found that the suspended aquaculture farms are more suitable for damping shorter waves, and it is not sensitive to water level change. However, the submerged vegetation is very sensitive to the water level change. So probably the optimization for wave attenuation is to combine these two kinds of materials. So in the future work, we will use our model to analyze more complicated vegetations like this with multiple branches or leaves. And our current study is for using the vegetation or aquaculture farms is more suitable for rural areas or the countryside. So for this protection for cities, probably we may use other methods such as this one we can consider the landscapes the view to take more views, and we can add floating pathways to enable public access to new front areas. So this is a project, Emerald project, that will be implemented in at Boston regions. Okay, so well, I think probably it's time up. So that is my presentation. Thank you very much.
Thank you very much. If we have any questions, feel free to use the chat if you're comfortable with that, or you can raise your hand using the reaction button, or feel free to just unmute yourself and ask a question as well. I have Brian DZ that has raised his hand. Go ahead.
Yeah, hi. Thank you for the talk today. Appreciate it. I think this some of these agricultural-based solutions to shoreline issues, I think, is a pretty cool way forward. Sort of green engineering, I think, is going to be really important going forward. And so it looks like you're doing some pretty neat work there. I have a question on some of your newer work. The erosion along the coast of, I guess it was Lake Michigan. It was pretty interesting to me. I was curious if you had any sense of, is there a key factor that's dictating whether you're losing or gaining sediment? It looked like some of the losses and gains could be pretty close together. Like there would be like a bright red or a reddish one next to a bluish one, like sort of, and it looked like the contrast could occasionally be sharp. And so I wasn't sure if there was a defining characteristic, or is it just like each parcel is just kind of has its own characteristics, and that, or if there is some fundamental character that's sort of really driving whether a spot is losing or gaining?
Well, that's a very good question.
Yeah, it's okay if you don't have the answer. You can just kind of, if you had a gut, what does your gut tell you? Like, what do if you have just general thoughts, it doesn't have to be perfect. I was just curious, like, you can see like right by letter 10, there's right by on the left side of on the left side of that plot, right? 10, it's bright red, and then next to it is blue and blue. And so I wasn't sure if, like, why is that one characteristic? Why is that one spot gaining sand while all the ones around it are losing? And I wasn't sure if there was something like specific, some characteristic that might make that one, or the ones that are like that, susceptible.
Well, so yeah, it just depends on the mesh of the model. So well, so usually, if the sediment is eroded at set spots, and the sediment will be transported to nearby cells. So usually, if this spot is eroded, probably the nearby budget cells would be deposition because the sediment transports. Yes, that's true. But if we were to resolve this very, the difference, probably we need to make a very fine mesh, and that'll be, computer expensive. So in our present research, we like to analyze the whole lake, so we can, if using a very fine mesh, that would be probably not possible for the computing. So if we like to, and this can give us a very general pattern of for the entire, for the lake-based erosion. But if we like to see if, for local side, probably we need to use small scale model and make a very fine mesh to see how the sediment is transported and reality. But well, thank you, Bryce. That's a very good question. But
no, thank you.
Yeah.
We have a question from Blair Morrison. Blair, if you'd like to ask your question, feel free, or I can read it as well.
Wow. Okay, so it's in the chat box.
Yes.
Wow. Where was? Okay, I will read this.
Okay, that's great.
Quick read out. So this is okay. This is very cool. Research. Okay, thank you. I currently work with aquaculture division for the state of Florida, and the department is looking into expanding program at a permit for seaweed and macroalgae, but cadavers must be native species. Can you speculate the wave attenuation properties of algae with different morphologies than kelp, like branching structures in gracilaria, short flat sheets in wow, this is a very good question. So in our present research, we use macro, that is sugar kelp, Saccharina latima, which is common in the coast of Maine. But for other kelps, actually, unfortunately, I'm not familiar with these two species, morphologies, branching structures in gracilaria. So that is short flat sheets. So for short flat sheets, if I understand correctly, so you mean the blade length of the species short. So for smaller balance, the wave attenuation would be smaller. But if the density, I mean, the canopy density, so if there are more species in one unit area, then that can get more wavelength. So I think the size, the canopy size would be the major factor to influence the wave attenuation. And also the vertical position of the aquaculture structures is also important. If the aquaculture structure is floating near the surface, it can get more wave energy. But if the aquaculture is at the bottom, probably it cannot reduce wave energy because the wave energy decreased along the water depths. Yeah, I think that's what I came up now. So, yeah, we can discuss more later if you have any more questions.
So also, yeah, kind of just seconds. And followed by the Blair's question and the Longhuan's answer, I think it would be a very nice job to do service right along the coast. So we can find we just need to build up a database, right? We need to have the type of the vegetation or the seagrass and like any parameter like drag force, like density or blend length. We can build a very nice, and also all kinds of aquaculture farms, right? Oyster farm, mussel farm. If we have then database or make a book, it will be easy to select, right? Suitable, solutions for each particular sport.
Yeah, thank you. Well,
another question. So I might have a question. So in your like erosion analysis, do you consider the wind direction?
Wind direction. You mean for what analysis?
In your like erosion, you have then
that you mean Lake Michigan?
Lake Michigan. So you have
wind stress, right?
Yeah, you calculate the wind stress, right? You have plot with the wind speed. So I just wonder, did you consider the wind direction? Does the wind direction affect the erosion or deposition along the shoreline?
That's a very good question. So yeah, I think the wind direction or the wave direction, of course, will influence the coastal erosion. So in this, so in our current research, we just want to show the relationship between the basin-wide coastal erosion and the basin-wide wind speed or wave heights. So we have not studied the influence of the wave direction on the coastal erosion yet. So yeah, but probably well, I think we have another. Hey, I cannot. Okay, so probably from this figure, we know that the erosion or the wind speed decrease in the Western Lake and in the Eastern Lake. So usually in Lake Michigan, the wind comes from the left, right? And the wind, when the wind, you know, from the land to the lake, and the probably the wind speed will have a big change. And we've just finished analyzed the magnitude of speed. Yeah, I think that's a very good suggestion. I will check that. So I cannot give you a good answer right now.
Okay.
Any other questions or comments?
All right. So also another question. So in your like the wave damping by the vegetation. So it is possible to consider also the 2D, like, so now it's usually a 1D, right? In the tank, when you do the wave tank, you do the test, like always the wave is from one direction, right? Yeah, here. So but actually if we do a farm, it's 2D. So the wind come from the wave come from multiple directions. So it is possible to extend your model to a 2D model, right? So the wind can come any direction. A wave can come any direction, right?
So that's a good question. So I think, well, so in the model, we derived the wave attenuation from the, the drag flux. So we assume that the wave dissipation is due to the drag, and the drag is, so for the 1D model, the drag is from one direction, and for 2D models, the drag should be, from two directions. If we modify the drag, by adding one turns from the other direction. So probably we can do that, but this an issue is that so for one direction way, we consider the for 2D, and the wave velocity would be, if the velocity is u and v from two directions, and we combine them together, that will be the square root of u squared and v squared, right? And we'll use this velocity to calculate the drag. I don't know if this is a nonlinear term. So if it is a nonlinear term, then we cannot use we cannot get the analytical solution. But if this is a linear term, then we can use this model. I mean, we can extend this model for the two directions. Does that make sense?
Yeah. Yes. And also follow the random wave, right? So in your random wave, right, implement the force also as a spectrum force, right? Put in the wave spectrum. So yeah, it's more like this one. So if in the open ocean or along the coast, the wave spectrum also has a direction, like theta.
Yes.
Right. So it's possible, like here. Let's show this slide. Also consider the direction in your spectrum, and make your form at the 2D, and also give out just output wave attenuation also as a function of the directions data.
Yes, I think so. Yes, it can be included.
All right.
But I cannot explain more because I know it can, because previous studies for the submerged vegetation, they have done that, and our model is extension from the submerged vegetation. So I think we can do it in the same way.
All right. Okay. Thank you.
Yeah. Thank you.
Well, thank you for coming. And if there are any other questions, you can feel free to stay on for a little bit. But we appreciate everyone's attendance here. And thank you, Dr. Zhu, for being here and for giving us this talk today.
Okay. Thank you for the invitation. Yeah.